I couldn't resist this cartoon. There he sits. My ex-girlfriend thinks I'm mean, and my current one thinks I'm average. Maybe you've set your bar too high. Get it? The bar on X bar? Okay, so speaking of couples and pairs, we're going to look at data that are paired, and that's basically when we collect our observations in pairs or they occur naturally. A lot of times this happens in an experiment when we're doing before and after, or if we have some sort of special blocking. I think of like if we have plants near the sunlight and plants away from the sunlight, they're both going to behave differently. So you might take one plant near the sunlight, give it your special fertilizer. The other plant near the sunlight stays as a control, so you would compare those two. All right. You can also arise from an observational study. So it's a form of matching. Once we know the data are paired, we can examine the pairwise differences. And it's because we care about the differences. For example, if I was looking at plants, some in great sunlight, some in not great sunlight, I'm going to get some big variation from the sunlight. But what I'm trying to look at is the impact of fertilizer. So if I take into account and just pair the matching samples and look at their differences, so differences for plants in sunlight compared to differences in plant for shade, then I'm taking out variation for shade and sunlight. So blocking and matched pairs, they're both kind of the same thing. Blocking is for experiments, pairing is for observations. So here, this is probably more of a pair. Let's say we wanted to estimate the mean difference in age between husbands and wives. Well, if you look at the box plot alone, you'll say, there's not much difference, right? If I did a t-test for the differences, probably would not come up as significant, right? So I'm not getting a lot of info from the box plot. But I think we know on average that wives tend to be a little bit younger than husbands, and that shows when I look at the differences in age for the individual couples. So I match the appropriate wife to the appropriate husband. And that makes sense because you don't have a lot of 70-year-olds marrying 20-year-olds, so you don't have a lot of these 70-year-olds marrying these 20-year-olds. It happens. In this data, we have a 20-some year difference, but normally that's not the typical. So the nice thing is when you take a look at just the paired differences, we're taking out some variation for the differences in overall age range for husbands and wives. All right, we still have pretty much the same assumptions and conditions. Well, the new one is paired data must be paired. Independence, well, the data itself is not independent, but the differences should be independent, okay? The nearly normal condition still holds, except instead of looking at a histogram of your two data sets, you're going to look at a histogram of the differences. So let's go ahead. We're going to do a t-test, and the model that we're using, I'm going to just use Y bar. You might see D bar. There's no, whatever symbol that floats your boat. The main thing is this is the mean of the differences. This is the mean of the differences, all right? And critical values calculated the same way as before. The standard error is calculated the same way. That should be an E. So first of all, is it random? Well, the volunteers are not random, but it is an experiment. We will be doing differences match pairs, so maybe that's not so bad, all right? But it's not exactly random. These are volunteers. Okay, independence. Well, in terms of the before and after, that's not really independent. But the differences that we might see among the different people, you could argue that that's independent. Now, we also need to check the nearly normal condition, which means we're going to have to graph a histogram of the differences. So I'm going to show you a quick way to get that. And what you're going to do is you're going to create a new list. So I already entered L1 and L2. So this is before, that's after. And I want to do L1 minus L2. So what you do is you actually get out of list and you go L1 minus L2, And then you're going to hit the store button to tell it where to put the answers. Now I'm going to put those answers in L3. Hit enter, shows the data it generated. If you go to stat and edit, there's your list of L3, the differences. So that's handy when you have a lot of differences to look at. Okay. Then we go ahead and we go to stat plot and we look at the histogram, make sure we have L3 and hit graph. And you can see my histogram. I actually did play with the windows already a little on this one. And it doesn't hurt to play with the windows because sometimes it'll look really weird and sometimes it won't look so bad. But this is good enough for our statistics purposes. It is roughly unimodal and symmetric. You could say, yeah, there's a gap there. And you are perfectly fine in saying, hey, I got a gap there. But it's roughly unimodal and symmetric. And that point there isn't way far away. So it's not that bad an outlier. Now they asked how much did it change? Well, to do that, it's probably appropriate to calculate a confidence interval. And it's pretty much the same. It's going to be the average of the differences plus or minus whatever your critical value is times your standard error. And your critical value is going to depend on your degrees of freedom and your confidence level. So coming back to this, we're going to go ahead and do a t-interval. Here's all my data and my standard error. And here's my t-value for 9. Now, how did I get that t-value for 9? Technically, your calculator will spit this stuff out, but there are going to be problems where you're going to have to calculate this t-value. So I'm going to hit second distribution, and instead of inverse norm, it's inverse t. And then I'm going to do 0.975. Why? Because inverse t and inverse norm are one tail, upper tail. So we test everything underneath that upper tail. I've got my 9 degrees of freedom, and I let it sit there and think. And I got basically the same answers I have on the screen here, which is a good thing. All right. The funny part is I'll do my t, to do your t-interval, you basically make sure you have your data, your list. My confidence level is 0.95 and let it spit out the interval. And now how do we interpret this interval? Well, we are 95% confident that 6 weeks of this exercise program can produce a mean decrease in resting pulse rates of between 1 and 4.6 beats per minute. Again, I added for males because I go, wait a second, these are only guys. I have no idea what it'll do for females. And we know there's a difference physiologically so that you could, guys lose weight more easily than girls, which is really annoying. So, okay, what can go wrong? Don't use a 2-sample t-test for paired data. Well, you can, but you're probably not going to find everything. You're probably going to fail to reject everything because it's hard to see some of these small differences if it's which really pop out for paired data. Don't use a paired t method when the samples aren't paired. Yeah, you got to figure out who is appropriate to subtract from who. Don't forget your outliers. The outliers we care about are known the differences. You should be plotting that histogram of differences. And don't look for the difference in side-by-side box plots. Again, the power, this is an incredibly powerful way to see tiny differences when you have